Okay, this is discussion 5.1 on balancing equations and reaction rates. So we'll do a little bit with balancing equations. That's kind of one of those things you just have to practice, and then we'll talk about factors that affect reaction rates. Okay, so when we balance chemical equations, our goal is basically to observe the law of conservation of mass. That's the whole point of this. And then we're doing this by making sure that we have the same number of each type of atom on both sides of the equation. Coefficients change the number of molecules, and this is what we change when we balance an equation. We cannot change the subscripts once we write an equation, because if we change the subscripts, we would change the identity of the substances. So all we can do is change the coefficient in the front. So let's look at some examples after we go over some helpful hints. First, when you balance, start with atoms that are found only once on each side of the equation. So hydrogen and oxygen will often need to come last for this reason. In combustion reactions, which is when I have a hydrocarbon reacting with oxygen to produce CO2 and water, balance in the order carbon, hydrogen, oxygen. If you end up with an odd number of oxygen on the product side, then you'll basically have to double all your existing coefficients. So you'll put a 2 in front of the hydrocarbon, double the coefficients on carbon dioxide and water, and then you should be able to balance oxygen. If you have a polyatomic ion on both sides of the equation, balance it as a polyatomic ion instead of breaking it into separate atoms. So like if you have phosphate, for example, you might say I have 1 phosphate on the reactant side and 2 phosphates on the product side, rather than breaking that down into phosphorus and oxygen. Check all atoms at the end to make sure we have the same number of each type of element on each side of the equation, and reduce coefficients at the end if needed. So instead of the coefficients being 2, 4, 2, you'd want them to be 1, 2, 1. Okay, so let's look at a few examples. So let's look at the first one. Now, we can start wherever we want. Let's start with oxygen. To balance oxygen, we would need to put a 3 on the reactant side in front of O2 and a 2 in front of aluminum oxide. Now, when we put a 2 in front of aluminum oxide, that applies to both aluminum and oxygen, right? Because we can't just have more oxygen, we have to have more of that entire compound. So now I have 4 aluminum atoms on the product side, so I need a 4 in front of aluminum on the reactant side. Now, number 2 is an example of the situation where hydrogen appears more than once on the product side. So ideally, we would start with something else. However, at the moment, both sodium and oxygen are balanced. So we have to start with hydrogen. Now, when I look at this, I would say, okay, I know because I have H2O on the reactant side that I have to have an even number of hydrogens on the product side. So I'm going to go ahead and start by putting a 2 in front of sodium hydroxide to give me an even number of hydrogens. So now I have 4 hydrogens on the product side. So I can balance hydrogen by putting a 2 in front of water. That gives me 2 oxygens on each side, and then I need a 2 in front of sodium to balance that. Number 3 is an example of one of those combustion reactions. So we're going to balance in the order carbon, hydrogen, oxygen. So I put a 7 in front of CO2 to balance carbon, and an 8 in front of water to balance hydrogen. Now, be careful when you count up the total number of oxygen atoms. It's really easy to make a mistake. I have 7 times 2, so 14 from carbon dioxide, plus 8 from water, so a total of 22, which means I need a coefficient of 11 in front of oxygen. All right, so let's do another one. Now, when I start this one, I put a 6 in front of CO2 and a 3 in front of water to balance carbon and hydrogen. However, when I look at my total number of oxygens, I have a total of 15 on the right. There's no whole number coefficient I can put in front of O2 to give me 15 oxygen atoms. So I have to put a 2 in front of the hydrocarbon and double the coefficients in front of CO2 and water. Then I have 12 times 2, so 24, plus 6 is 30 oxygen atoms on the product side, so I put 15 in front of O2. Now, number 5 looks really complicated because there's a lot going on with all those polyatomic ions. However, it's actually pretty straightforward as long as you look at the polyatomic ions as one unit. I also think this is a good example of a place where you really need to go atom by atom or ion by ion rather than trying to look at the whole thing and figure it all out all at once. So I'm going to start with sodium because it's first. To balance sodium, I'd need a 2 in front of sodium phosphate and a 3 in front of sodium carbonate because that gives me 6 sodium atoms on each side. So now, at the moment, I have 2 phosphate ions on the reactant side and I have 2 on the product side. So that's balanced. So let's look at calcium next. I have 1 on the reactant side and 3 on the product side. So that means I need a 3 in front of calcium carbonate. Now I have 3 carbonates here and 3 carbonates on the product side, so the equation is balanced. So when you take it step by step like that, that's actually not such a hard equation to balance in the end. Okay, so now let's talk about reaction rates. So the rate of reaction is the change in the amount of a product or reactant over time. One really common mistake people make is that when they're asked for a rate, they tend to just say how long the reaction took. They tend to just give time. Okay, but that's not really a rate. If you asked me my rate of speed coming to school this morning and I said 10 minutes, well, that doesn't really give you the information you're asking for, does it? So we have to have that, the amount that reacted in a given amount of time. And this just tells us something about the speed of a reaction. So mathematically, we could express it as delta reactant over time, delta meaning change, or delta product over time. So there's any number of possible units depending on what we're measuring. Sometimes we would measure amount in grams or milligrams. If we were, for example, collecting a gas, we might measure it in milliliters. And the unit of time just depends on how fast or slow the reaction is. Most often for reactions we would do in class, we would use seconds, but we could use minutes, we could use hours, days, it just depends on the reaction. Now, there are 4 major factors we're going to talk about that influence reaction rate. And they're change in temperature, surface area, concentration, and the presence of a catalyst. Now, when we talk about rates, we're going to talk about something called collision theory, which has 3 major principles. The first is that in order to react, reactants have to collide, right? They have to be in close proximity or they can't have a reaction. The second is that they have to collide in the correct orientation. And finally, they have to collide with enough energy to overcome activation energy. So you learned about that in biology, so we'll revisit that in a little bit. All right, so if I increase the concentration, that's going to be one factor that causes a change in reaction rate. So first, let's define what concentration is. So we're going to talk about this mathematically and give more specifics later in the course, but for now, we could just say that concentration is the number of particles in a given volume, okay? So as concentration increases, rate increases. Let's think about why that is. Imagine that we all put on blindfolds and started wandering around the classroom. We would collide with each other, correct? If we invited another teacher's students to come put on blindfolds and walk around, we would collide more, right? Because there are more people in the same volume of space, okay? So likewise, if there are more particles in a given volume, that means there are going to be more collisions. Okay, now, we can also change the surface area to affect the rate. So first of all, how do we increase the surface area? So we can do this by crushing, chopping, grinding, etc. Basically, we're taking a large piece of something and breaking it into smaller pieces. The verb you would use would just depend on the substance you had. You can think about this with cooking, right? If you have a large piece of something that you want to cook, it'll cook much more quickly if you chop it up rather than trying to cook it as one big piece. So as we increase the surface area, the rate of reaction increases, okay? And the reason for this is that we have more particles available for reaction. All that surface area that was previously sort of hidden inside the larger piece of material is now available. So there are just more places for a reaction to occur. Finally, we can increase the temperature. Now, as temperature increases, we know that molecules move faster, right? Temperature is just a measure of the average kinetic energy. So 2 things are going to happen. The rate will increase because, first of all, more collisions will occur. Imagine again that we're moving around the classroom colliding with each other. If we start running, we're going to collide a lot more, right? Additionally, we're going to collide more and we're going to collide at much higher speeds, so we're going to have greater energy. So the collisions are going to have more energy, and as a result, the collisions are going to be more likely to have enough energy to overcome activation energy. Okay, so there's really 2 things going on there when I increase the temperature. Finally, let's talk about adding a catalyst. So a catalyst is something that speeds up a reaction but is not changed or consumed by the reaction. So let's think about how a catalyst works. So a catalyst provides an alternate reaction pathway that requires less activation energy. So this is an example of a potential energy diagram that shows that the reactants have a certain amount of energy, as do the products. And you can see in the blue is the activation energy without a catalyst. But when we add a catalyst, there's a much lower activation energy. So a catalyst doesn't give energy to the reactants, but it allows reactants that would previously have not reacted to react. So reactants that would have previously just collided and bounced off each other and not had a reaction, now they have sufficient energy to react. Okay, so pretty short discussion. See me if you need help with balancing. It's the kind of thing that if we sit down and work on it, I'm sure you'll be able to do it And let me know if you have any questions.